Hello, and thank you for joining us. Today's webinar is Low-Level Sample Introduction to ICP-MS with the MVX 7100 Workstation. Our presenter today is Dr. Pete Winship, Technical Product Manager for Teledyne CETAC. Please feel free to submit questions throughout the presentation, and a staff member will respond via email within a couple of days. Also, this webinar is being recorded and will be available for viewing within a couple of days. You will receive an email notification of its availability. Now I'll turn it over to our presenter, Dr. Pete Winship.
Hello. Hi. Thank you very much for joining me today. My name is Pete Winship. I'm a technical product manager at Teledyne CETAC Technologies. And one of the systems that I'm responsible for is the MVX 7100 microliter workstation, which I'm going to essentially introduce today and talk through the basics behind this. So I shall make a start running through. So what you'll see here, this is the MVX 7100 system. So this is what I'm going to talk to. So just a photograph of it, of the system here, so that you know what we're talking to. For this webinar, I'll just take you through a quick agenda. So start with what this system is, the MVX 7100 and what it can do. I'm going to then go through just a quick description of why we developed the system, to give you some background, and why you would use this system with ICP-MS instrumentation in your laboratory. Then I'll go into a hardware tour just to take you through sort of the key components and the features and function. Beyond that, I'll go into a description of generating data from a limited amount of sample volume and what that might mean. I'll touch briefly on some advantages of introducing lower sample volumes intentionally into your ICP-MS, because there are some advantages of going in that direction rather than having to do it as a necessity. And so I'll touch briefly on that, and then I'll go through some applications and some examples that we've been seeing in the field, that we've been doing ourselves, and that we've been doing with either collaborators or with customers. So I'll start with what the system is. What is the MVX 7100 microliter workstation, and what it can do. So this system is it's an advanced auto sampler for ICP-MS, and from a sample introduction point of view, it allows the operator to introduce what you might refer to as low volume samples. So low volumes, so we're talking here of tens or hundreds of microliters that you might have, that you might be looking to generate data from. You might use the MVX for working with what you might refer to as suboptimal sample volumes. So a sample volume where you just have a little bit less than you need. So just less than you would typically run with standard automation. So we might be talking about 1 to 2 milliliters here, or a bit less than that. The sampling range for this system is approximately 5 microliters up to about 1 milliliter. I've personally generated data from 2 microliters with a multi-collector system and the MVX, but about 5 microliters up to 1 mil. And then with that sample volume, you can introduce it to ICP-MS within pretty much whatever flow rate that you want. So down to 5 microliters per minute, which is down into the total consumption range, up to flow rates far greater than you would ever need for nebulization in ICP-MS. So in addition to the sample introduction side, the MVX can also be configured to support sample introduction to ICP-MS generally with in terms of things like sample homogenization. So if you need some homogenization, some mixing, some turbulence in your sample immediately before sample introduction, that can be offered with this system. There's an option for temperature control if that's required, particularly for very low sample volumes. That might be a necessity. There's septum piercing capability if you've got sealed vials. It's compatible with well plates, and it can be configured to add additional modules with additional flows, etc. And then the washout, the rinsing between samples can also be configured depending on the kind of work that you're running through. So that in a nutshell is the system, what it can do for ICP-MS and some of the function behind it. But I'll be going into this more specifically as we go through. So, hold on. So why did we develop the MVX 7100 system, and why would you use it? Well, what we found was that at conferences or talking to people, we were coming across the same question, which was in terms of sample introduction to ICP-MS. This question was coming up of what can I do with a sample where you've got a very small volume or a small mass that's already containing elements of interest at trace levels. So with that question, there are some obvious answers to that. So the solution might be, well, you could take your sample, and if it's a solid sample, you could do a digestion followed by dilution, or if it's a liquid sample, you could just do a dilution to get more liquid to work with, more sample volume to work with. That's an obvious thing to do, but in the case of having element analytes of interest already at trace levels, then there might be some issues of sensitivity. So that might be applicable to some samples, but not others. You could use a low flow rate nebulizer, say with under self-aspiration, which again might be suitable for some samples, but not all. There might be other analytical considerations as well. And I have to consider matrix matching, which might cause further limits on the kind of sample volume that you can work with. And then there's other automation. So at the time we looked into this, there were limited options available in a non-metallic form. So this problem we kept hearing fairly regularly at conferences, talking to customers, etc. And it wasn't just there in the literature as well. The question kept coming up, or the point kept coming up. So just to give you an example, there's a review paper by Teledyne and Mermet from 2006, as well as other publications as well, which focus on certain sample sizes, sample volumes, sample masses, which might be challenging to analyze with ICP-MS. The table here contains data from that publication, and one of the concluding statements from that review paper was that there are many fields in which the available sample volume is the limiting factor in elemental analysis. So we went from here and we started putting some thought into this, and ultimately went down the road of developing the MVX 7100 system. So just to sort of position where this is, and to give you an idea of what some of the limitations might be with low volumes and where the MVX comes into this. I'm just going to give you an example, sort of a thought process really. So what I've got here is a diagram where the line at the bottom is the sample working volume range, so the amount of sample solution that you might have to work with. So going from left to right, low to high. On the right-hand side here, we've got a diagram of what you might call a standard auto sampler for ICP-MS. This is our ASX 560 system. And for that system, you'd be looking to introduce sample volumes via a peristaltic pump to an ICP-MS within the range of, say, about 1.5 milliliters at the bottom end, perhaps, up to and greater than 50 milliliters. But as you go down that volume range, down towards that 1.5 milliliters, so say you're in the range of 1.5, 2 milliliters, that kind of scenario, you might find yourself in a position where you have to compromise on the data that you're looking to generate. You might not have enough to do certain things for your analyte suite, for replicates, etc. So we developed the MVX 7100 system to sit on the other side of this line to cover this compromise. So we developed this system with an ability to cover sample volume ranges far lower than this, and then to sort of hand over in that compromise region. So we go over to the other side of the line now to the MVX 7100, which is the diagram on the left. And the sampling volume range, as I mentioned before, is down at the 5 microliter end up to greater than a milliliter. So that covers this range of compromise where you might have an issue with standard automation or with certainly with lower volumes. So why use this system? So I've talked a lot so far about low volumes, suboptimal volumes. You, as an operator, as an analyst in a lab, an operator of instrumentation, you might just not have enough sample volume to work with. So you might be in a scenario where you would need something like the MVX because you've got a limited amount of sample available. Your samples may also be precious in nature. They might be part of some sort of research project. They might be costly. They might be something to do, again, in research. You might have a scenario where your samples are very valuable based on what you're doing. You also might be in a scenario where if you have a limited amount of sample volume, you might not be able to repeat your analysis. You might not be able to have a second bite at the apple, so to speak, to get the same data or to clarify the data that you've already generated. So that's looking at using the MVX almost as a necessary tool to analyze sample volumes that you might not have enough of. Also, I'm going to get into this in a bit more detail later on, but you also might be in a scenario where introducing low volumes of a sample actually might be beneficial. So you could use the MVX from that point of view as well. So you might be looking to reduce the volume of expensive reagents that you're using. You might be looking at reducing the amount of waste that's generated through sample introduction. So reducing the amount of waste which just goes to drain. You also might be looking at doing something like reducing the exposure of your interface cones to a certain sample matrix. Again, I'll get into that later. In addition to that, with the MVX, you by the way that you're running it and by the way that the tubing is the materials the tubing is manufactured from, it's an alternative to what you might refer to as the standard automation approach to ICP-MS. So with the MVX 7100 system, there is no soft peristaltic pump tubing as part of the sample introduction process. So therefore, the system is compatible with certain sample matrices, more challenging reagents that typically cause a problem for peristaltic pump tubing. So, for example, concentrated organic solvents, say something like xylene, for example, or the NNP solvent, which is typically used in the semiconductor industry. So you can use the MVX 7100 for batch analysis without having to dilute those organic solvents. You've also got access to septum piercing capability. So if you want to have a sample which is in a sealed vial, sealed container, you can pierce a septa to take the sample from it. So this would be beneficial for samples where you've got issues with evaporation or in terms of the sample matrix or the analytes of interest. So moving on, I'll now take you through essentially a hardware tour of the system and what the features and functions of this system. So going back to the original photograph of the MVX 7100 system, which I showed in the beginning, I'm going to stick with this image, and I'm just going to walk you around the main components of this and walk you through how a sample introduction works. So to start off with, we have a central piece of automation. So the main section in the middle of this system. So this is one of our ASX 7100 auto samplers. So this is an accurate and precise 7000 series based auto sampler, which has the accuracy and precision to be able to take a sample from a 384 well plate. So that's the accuracy and precision in all three dimensions, the X, Y, and the Z, to be able to sample from a very, very small well, from a 384 well plate repeatedly. So this is the central automation. Now, what I show here on the right-hand side of the automation, it doesn't matter which side because these modules can go on either side. On the right-hand side here, this is a valve syringe module. So this module is responsible for the sample uptake. So this is going to take your sample up from its sample vial or well plate well and take it away for analysis. So on this module, you've got two key components here. On the bottom of that module there, you've got a syringe pump module, a short syringe pump a syringe pump there. So this short syringe is responsible for pulling the sample from the sample needle or the probe and pulling it up onto a sample loop, which is positioned on a 6-port switching valve, which is highlighted above the syringe pump. So you've got, because it's a syringe pump and because this is all controlled by software, you can pull your sample up at whatever speed you like and determine the sample volume and position it where you want on a sample loop. All of the tubing in this process, metal-free, so it's a metal-free flow path. So the materials of that flow path are quartz, PEEK, CTFE, otherwise known as KELF, and PFA. On the other side of the system, you have another module. So again, it doesn't matter that it's on the left-hand side. They're interchangeable, so they can go on either side. So this system is therefore compatible with all ICP-MS instruments that are on the market. So on the other side here, you've got this other syringe pump module. So it's just a syringe pump. There's no 6-port valve on this side. Now this syringe pump replaces a peristaltic pump for sample introduction. So it's this module which is going to push your sample out of a sample loop, which is on the 6-port valve on the other side, towards a nebulizer. So, so what's going on here is after the on the other module, the sample's been pulled up onto the sample loop, that 6-port valve will switch, and a flow from this syringe pump module here with the longer syringe is going to push your sample to a nebulizer at a flow rate which you determine. So the analyst, the operator who's operating this automation and an ICP-MS will have a introduction flow rate in mind. It might be anything from down to the 5 microliter per minute level up to something more like 500 microliters per minute. That will have been determined, and this pump will push the sample at that flow rate to the nebulizer. Again, like the other side, it's an entirely metal-free flow path. So in this case, the materials you're looking at, the quartz is for the sample, is one of the options for the sample probe, the sample needle. In this case, all of the tubing from that module to the rest of the system is PEEK, CTFE, and PFA. Right. On the front of the system here, so we'll go to sample rack options. So what we're looking at here is the options available are 1.5 milliliter HPLC vials, so those are the VT54 type. You can work with 96 well plates of various capacities, so there can be or there could be the tall 44 millimeter height high capacity well plates, where the well plate wells have a capacity of about 2 milliliters. So it covers that full range. You've also got access to 3 hoops, where those well plate wells are very, very small in capacity. And you can also work with microcentrifuge tubes. So if there was a requirement for centrifugation of a sample, you could use those tubes, spin them down, and then you could sample from whatever height you wanted in that tube. Also on sample racks, you've got the opportunity for temperature control. So there's an optional temperature control module here, a Peltier rack module, which can sit underneath the sample racks or the well plates and provide temperature control down to 4 degrees C or up to 40 degrees C, and then anything in between. So you could have cooling, you could cool the samples to minimize sample evaporation or stabilize a volatile sample matrices like an organic solvent, or an analyte which is known to be more volatile. Or you could use heating for incubation of a sample or samples, or to prevent solidification. For example, the best example of that is DMSO, one of the solvents often used in the pharmaceutical industry, has a solidification point close to room temperature. So it's being able to heat a sample solution like that and maintain it at a certain temperature, so above room temperature, is a good approach to make sure that your batch analysis can continue unhindered. Sorry. All of this is software controlled as well, so you can have everything maintained in your operating software. And then just on the other side of this, there is a dual rinse station as primary or secondary rinsing for your sample probe, or you can rinse with different reagents. So again, you can configure your system to the kind of analysis that you're doing. So following that, as a hardware tour, how does the sample introduction process work? It's actually very simple. So I've pretty much alluded to it as we go through, but I'll just walk through this again. So there's 2 stages. There's a sample loading stage and a sample introduction stage. So we start with what we've got here is we've got 2 flows going on at any one time. You have a flow from the syringe pump module, which is the module which is delivering the sample and a carrier solution to your nebulizer. This is shown in blue on this diagram here. So that flow will can either be set so it's a continuous flow through to your nebulizer, or it can start after the sample's been taken up. But that flow goes from that syringe pump module through along the blue line via the 6-port switching valve on the valve syringe module to your nebulizer. So whilst that flow is going, you've got the other flow here, the green line flow. So that goes, if you go to the actual automation, which is called MVX 7100 microliter workstation here, the sample probe or the sample needle can move and go to a particular sample, and by action of that short syringe on the valve syringe module, it can pull the sample up, shown on that green line, and pull it onto the sample loop, which is shown on the 6-port valve. So when the sample is on that 6-port loop, that 6-port switching valve will switch, and then we move on to the next step, which is the sample injection. So the color of the lines swap here. So what happens then is your sample that was on the 6-port valve on that sample loop is then pushed via the syringe pump module to the nebulizer. So we're following the green line again for the sample going to the nebulizer. Now, whilst that's going on, the sample is pushed off the loop with a carrier solution behind it. That carrier solution has 2 functions. You sit through the nebulizer. The other is to wash the sample loop behind the sample. So there's an excess of carrier solution going through that line to the nebulizer. And again, that's at whatever flow rate is required and determined by the analyst in the lab. Whilst all that's happening, we go back to the short syringe on the valve syringe module. That will backflush through the line in the 6-port valve, back through the sample probe into the rinse station. So we're washing out that line where we've originally taken up the sample. We backflush through, and we can configure that backflush so to make sure that we go back to baseline for the next sample. So if you've got a sample of or a known memory effect, for example, you've got analytes of known memory effect, then you can configure this so you can really push that. You can configure the washout to make sure that you flush out and rinse out any contamination, any background from that line before the next sample. So that's how the system works. Now, I've talked a lot about the nebulizer in this case, pushing towards the nebulizer, which opens up the next question. And that question is, well, what kind of nebulizer can I use? So if I go to the next slide, essentially the answer is any type. The MVX 7100 microliter workstation is compatible with, I'll say, most nebulizer types. I've not come across a nebulizer yet that you can't use. So I wouldn't like to say all types, but it's pretty much all types. It's certainly most types of nebulizer. So the flow rate, introduction flow rate that the MVX 7100 system can deliver covers the introduction range for pretty much all nebulization that you would require for ICP-MS. So going down to the 5 microliters per minute, that sort of range, 5 to 10 microliters per minute covers total consumption. So where you are introducing a very small amount of sample liquid to a nebulizer, and you're not sending anything to drain. So you're going all the way down to the total consumption end, and then up to much greater flow rates than you would need for nebulization, up to the higher end, what you might refer to as standard nebulization. So that might be anything up to 500 microliters per minute, up to a milliliter per minute, and beyond. So just to show you on the images on the right, these are nebulizers that we can provide. The C-Flow PFA nebulizer, that's available in, we say flow rates of 50 microliters per minute, 100 and 200 microliters per minute. And then you've got the DS5, which is a total consumption nebulizer. But these types of nebulizer are all compatible with the MVX. So the next section I'm going to move on is the idea of generating more data from a limited amount of sample. So we developed this system primarily to overcome the problem of having a limited amount of sample volume, or a very small mass of sample that could be digested. But what we've found is we've really spent more time with this system in different laboratories of approach to samples with the MVX. One is overcoming the problem of a limited amount of volume. The next one actually is generating more or optimum or even superior data from a limited sample volume. And so that's what I'm going to focus on next. And then I'll briefly touch on using the MVX and low volume to overcome some challenges posed by some sample matrices. So I'm going to focus on this one next, generating more optimal or superior data from a limited amount of sample volume. So what can often happen in trace element laboratories, and I've certainly been in this position, is being handed a sample, an analyst in a laboratory being handed a sample and being asked the question, what kind of data can I obtain from this sample volume? So what can I do with this low volume? What I'd like to sort of steer your thinking, I'd like to steer your thinking away from this as a question and actually change that question, because with the MVX, you've sort of got to work backwards, if that makes sense. So instead of that question, what can I do with this low volume? The question should instead be, what do I want to achieve from this low volume? So you work backwards. What is your wish list for your sample? So you work backwards, what do you want? And then you work out how you can do that with the MVX and the low sample volume. So you start off with the question of measurement time. So in ICP-MS, you have measurement time which corresponds to what you want from your sample. So you start asking a number of questions. What kind of data do I want from my sample? What size of analyte suite do I want? So how many elements am I interested in generating data from? How many isotopes is that? Do I want three replicate measurements for each element, or do I want 5? Do I want 7, etc.? What do I want from it? Are there different gas modes required certainly for quadrupole-based ICP-MS? So for overcoming polyatomic ion interferences. And then do I want to repeat the analysis of the same sample? Do I want to do it twice? Do I want to do it 3 times? So you start with those questions, and all of that added together corresponds to the measurement time that's required. So you start off ascertaining the measurement time from your ideal scenario of what you want to get out of your sample. And then you work it through. So you start off, you know the measurement time that you're interested in obtaining, you know the sample volume that you have, and then from there you can establish what introduction flow rate that you need to be delivered by the MVX through through an appropriate nebulizer, and then you can realize the data that you want from this. So again, just a further example. So this is a trace. This is some real-time analysis data from a multi-element standard. So this is 1 part per billion multi-element standard, which most people in an ICP-MS laboratory are familiar with. This kind of trace. So we took, just to give you an idea of really how much you can stretch out low volume. We took 100 microliters of this multi-element standard, and we introduced that through what you might refer to as just a standard concentric nebulizer, advertised as a 400 microliter per minute concentric nebulizer. So we introduced that 100 microliters of sample at a flow rate with the MVX at 200 microliters per minute. So from that, there's a growing period, there's a washout period, but in the middle, there's that period of stability where you take your measurement. So from there, we got 21 seconds of measurement time for 100 microliters, which might be plenty if you were interested in only a couple of analytes, a couple of isotopes. That might be perfectly fine. But you might have wanted more than that. You might want more analytes. You might want more replicates. You might have different gas modes. Therefore, you would need more than 21 seconds. So let's go to the next slide. So if you reduce the introduction flow rate, you take the same sample volume, you introduce it via the same nebulizer, and at a slower flow rate, we go from 21 seconds and all of a sudden we've got 31 seconds. So we're getting more out of the same sample volume. So again, that might cover the analytes that you're interested in. It might cover the replicates that you need. It might not. If it doesn't, then you can slow it down even further. So as we go through this process, we can go further and further and further, slow it down. And essentially what I'm showing you here is how you can take a very small sample volume, you can stretch that out, and you can achieve the data that you want. Now, there is a slight payoff here. So as you do this, so in this case, we've gone to 100 microliters per minute. We get more measurable data out of this, so we're now at 48 seconds. There is a payoff here. You are sacrificing some sensitivity as you do this. However, modern ICP-MS the latest generations of ICP-MS have got more and more sensitive, so it allows us a lot more room to work and to operate and generate the data that we want. So we're currently at 100 microliters per minute. So let's drop it to 75, and all of a sudden we've got 64 seconds of measurement time from 100 microliters. And we can keep going. So I believe that the last one that I ran for this, so this was just in our laboratory and our facility in Omaha that we generated this data. So we get to 50 microliters per minute. Again, this is through the same 400 microliter per minute nebulizer, 100 microliters of sample, and we're now at 103 seconds. So a minute 40, a minute 43 seconds. So with a minute and 43 seconds, we could have introduced 100 microliters of sample, and we could have had quite a large analyte suite from this. We could have had multiple gas modes for overcoming polyatomic ion interferences, and we could going through this process, optimizing this and getting the flow rate right, we can realize the kind of data that we want from a low volume. So it takes me back to that question again of what data do I want from my sample, rather than what can I do with this tiny volume. So the next stage I'll move on to is what you might refer to as the advantages of introducing a lower sample volume. I'm not going to dwell a lot on this, but it's essentially food for thought. And just to give you some ideas as to where we've the markets that we've gone into, the MVX 7100, and this will sort of feed into the section that follows. So in addition to handling low volumes, you might look at using the MVX for overcoming certain challenges. So there are certain sample types where sample volume is never really a problem. You will never be in a position where you don't, you have a tiny amount. You might be, but there are certain sample types where there's an abundance of sample volume, but the sample matrix actually might be the bigger problem. So I'll give you two examples of that. One is seawater. We won't run out of that in a long time. And petrochemicals. We can have quite large sample volumes of both of those types, but they pose matrix challenges to ICP-MS. So what we have found through work with collaborators, through data generation, we've found that actually intentionally going to low volume sample introduction and lower flow rate sample introduction, we found that there are analytical benefits from doing that. So for example, the one that immediately springs to mind is an improved limit of detection. We've certainly seen that in petrochemicals, where you take something like a crude oil diluted in xylene. If you start introducing 100 microliters, 200 microliters, 300 microliters into a plasma, the limits of detection of your analysis considerably improve because you're introducing much less organic solvent, you're affecting the plasma much less, so your analytical capability actually improves. The same can be said of seawater. This is something else that we've seen as well. So a concentrated seawater introduced to an ICP-MS with a marginal dilution for adding an internal standard, teed-in internal standard flow, we've actually seen a minimized signal suppression from the salt in seawater. So there are considerable advantages for some sample types to going to this low volume, low flow rate approach. And because of that, because of putting less sample in, lower flow rates, you're essentially making your analysis more robust. So for example, if you work with the seawater and put less sample into your plasma, you can do that for a much longer period of time rather than introducing several milliliters of sample for every sample that you're working with. Then you can start looking at the opposite side of this as well. So if you go to low volume, low flow rate, your waste that you're generating can come down. So for certain sample types, that's very beneficial. So for example, in the nuclear industry, cost reduction comes into this as well, and you can get improvements to safety. Again, the nuclear industry is one of those examples markets. So I don't want to focus on that too much, but that is an area that does interest us, and that this feeds into applications and examples, which is where I'm going to finish off with for today. So as I mentioned, we started going down this road with the MVX of using it as a tool to overcome the challenges posed by limited volumes. But we've gone into areas, sample types, and markets that we never really considered when we started this. So I'll start off with one of the common areas for this kind of work. So biological analysis, clinical research, clinical development, etc. So I'll start off here. There's a number of common clinical or biological sample types that are applicable to ICP-MS, where the MVX can certainly offer an advantage. So bloods and blood serum, this is a type of analysis in ICP-MS for a lot of different laboratories, but typically there is an abundance of sample volume for that, so there's no issue there. However, there are some legal limitations on that kind of sample when you start considering babies and infants, for example. Is in a, for example, immunocompromised or something like that, taking actual samples is going to be more of a limitation. So in that case, the MVX can come in and can start actually being an advantage to that kind of sample problem. Blood spots is another example of this, and you can see on the image on this slide on the top right, that is a heel prick test card. Now this might have different names around the world. In the United Kingdom, this is called the heel prick test, where a newborn baby will have a blood sample taken. They essentially have their heel pricked, and a small amount of blood is spotted onto one of these test cards. So I believe the test is for some sort of vitamin test, but there's an excess number of spots taken, and in this case, what's been done with this kind of sample here is, with these test cards, punches have been taken from the card of about 7 millimeters across. Those punches from the card containing the blood have been digested. So essentially, you've taken the punch, you've digested it and put it into a liquid, and the amount of liquid made available from there is about 500 microliters. So you can start incorporating the MVX into your ICP-MS analysis to overcome that kind of challenge in that kind of laboratory. So a blood spot, another example of this. Urines, again, there's not typically a problem with sample volume there, but there might be in some cases when you're looking at certain studies, particularly involving animal studies. Tissue biopsies, again, there can be limited material taken from the point of view of the biopsy. So again, you can take that limited amount of material, do a digest, and take the small amount of liquid that you get from that and introduce it to an ICP-MS via the MVX. Cerebrospinal fluid, again, there will always be a limited volume there, and that's something that's of interest to some of our collaborators currently. And then cells. Now, this is an area in of itself, the single cell analysis, which I delivered a webinar on a couple of weeks ago. So there's a separate webinar for this. I won't go into cells so much, but there's a separate webinar for this that's available via our website. So that's biological and clinical. Geochemical analysis. This is an area which we've been involved in fairly heavily over the past few years. what we've found is that, again, going to low volume, low flow rate is beneficial for other reasons. And in multi-collector ICP-MS, going to that approach, low volume, low flow rate, for isotope ratio analysis, actually gives you a superior isotope ratio precision. So what you'll see here is there's a couple of photographs on the right of multi-collector systems, and then there's the graph in the middle of this slide, which shows precision for isotope ratio for 2 uranium isotopes. That's 235 to 238. So what you've got here is that you've got the blue crosses on the right-hand side of that chart. That's repeating data from what you might refer to as the conventional approach, which is natural aspiration with a self-aspirating nebulizer. And then the data in green, the green crosses there, that's data generated by the MVX 7100 system. So what we're showing here is through sample introduction to a multi-collector ICP-MS, the measurement precision at 2 relative standard error is actually tighter, it's more repeatable, and it's better data, it's improved data compared to the conventional approach. So from the point of view of geochemical testing and certainly geochronology, that is a considerable advantage. Added to that, because you're working with an automated system, there's a lot more control over this, so there's less sample used, there's less waste generated, and it's actually faster throughput. So you're working through samples in 8 to 10 minutes per sample rather than half an hour. And then this approach is also applicable to nuclear analysis, where there's work on isotope ratio, work with multi-collector, as well as geochemical. So in addition to that, there's another example here. It's in the geological field, but it's more applicable to other things as well. So what we have here on this slide is this is a scenario where you have a small sample mass and you are digesting it into a small liquid for analysis. So in this case, we're talking about micro drilling. So in geological terms, you might be interested in something that has different growth bands. So that might be a speleothem or a shell. So you might be removing certain sample masses, so micro drilling, removing material that you're interested in analyzing, digesting that, and then introducing it in a small volume. And a good example of this is work that's taken place between the British Geological Survey in the UK and the University of Bangor in the UK. And then, excuse me, on the right-hand side here, you've got a graph which has data from a whelk shell, a whelk shell global warming study, where whelks have been studied for their growth over the years in certain different conditions. So these shells have been taken, certain sections of the growth bands have been drilled out, and then they've been digested and analysed, and they can correlate those growth bands with different environmental conditions. So in this case, what you're seeing here on the graph on the right-hand side, this is iron analysis through these growth bands, and you can see that the amount of iron in the different areas of these bands changes over time. So what they know here is that the growth bands correlate to certain ages and so what you've got here is at the start of the early years, you've got a higher concentration of iron, and as the whelk gets older and the conditions are changing, you go to a lower amount. So there's a lot less 2 years later. Excuse me. I've also mentioned petrochemical so far, so I'll just mention this again. Petrochemicals and solvents, this is another area that we've found is it's beneficial to work with the MVX. Not so much for a scenario where you have a limited volume or a limited mass, but more from the point of view of introducing less sample to the plasma and improving the quality of your data. or using it from a different point of view, like overcoming issues of sample evaporation. So in the case of organic solvents and petrochemicals, you have a large amount of carbon in these kinds of samples. When these samples are introduced to an ICP-MS, you get a lot of carbon deposition on the interface cones of your instrument. Organic solvents, petrochemicals might not be particularly friendly to peristaltic pump tubing. So peristaltic pump tubing can be degraded through analysis with standard automation. There's obviously issues with evaporation and losses and signal stability as well. So what we've found is, working with the MVX 7100 system, this system can address a lot of those challenges. So in the case of low volume sample introduction, you're introducing less carbon essentially to your ICP, so there'll be less deposition on the sample cones, which means a number of things. One is that they'll last longer, so you don't have to take them out and clean them or replace them. So there's a cost implication there, there's a cost saving implication. There's no peristaltic pump tubing associated with the sample introduction process. It's all PFA tubing, so it's more resistant to those two organic solvents if you want to analyze them in a concentrated form. You could use sealed vials, so the VT54 type vials with septum piercing, or temperature control, or both of those, and that will then inhibit sample evaporation, so you're improving the robustness of your batch analysis. And then less organic matrix being introduced to the plasma at any one time, so you do have an improvement in signal stability, an improvement in detection limits. In this case, you'd be looking at introducing at flow rates in the microliter per minute level rather than the milliliter per minute level. So there are considerable benefits in petrochemical analysis for this. So just some examples of those kinds of solvents. The NMP solvents, this is a solvent commonly used in the semiconductor industry as well as many other industries. That kind of solvent will quite happily, in its concentrated form, chew through peristaltic pump tubing very quickly. There are applications where you can dilute NMP, but again, you might not want to do that, certainly when you're doing quality testing analysis. Xylene-based matrices for petrochemicals, crude oils, biodiesels, etc. Again, xylene tends to make peristaltic pump tubing stiffen and brittle. So you might want to avoid a peristaltic pump and move to something like this kind of system for sample introduction. And then there's a recently generated ASTM method exactly on this kind of work for ICP-MS with middle distillate products, where the MVX 7100 would be beneficial in that kind of analysis. Right, and then there are numerous other applications that I could talk about, but I'll just finish on two last points really. The pharmaceutical industry is another area where the MVX would be beneficial. You're going to have some scenarios of limited sample volume based on cost, maybe in R&D, maybe in new formulations. So that would be beneficial in that case. DMSO is another one of these solvents which is typically used in the pharmaceutical industry. And unfortunately, DMSO has, I mentioned before, a solidification point just shy of room temperature. It's about 20 degrees C, I believe. So you've got a scenario where if you have a colder day in the lab, you might end up with a problem in terms of sample introduction or in your nebulizer, for example. So you could use the MVX to work with less sample if you're using DMSO as a solvent, and you could control the temperature prior to sample introduction, hold it at about 30 degrees C for the sake of argument, and that way you're going to make sure that your sample goes through into your nebulizer, doesn't solidify, and it ensures the robustness of your analysis. And then the nuclear industry, much like the geochemical industry, geochemical analysis, you might have multi-collector instrumentation you're interested in operating. With the MVX, you can introduce less sample. There'll be less waste generated, which has cost implications. It'll be safer because you're using less material, less less sample. So there are considerable advantages to operating the MVX 7100 in that industry. So I'm going to end it there for today. If anybody has any questions, please feel free to email me. I'll put my email address is on the end of this presentation. I'd just like to acknowledge quickly our associates at Agilent Technologies and at Thermo Fisher Scientific, our collaborators Lewis Banks and Matt Horsted at the British Geological Survey, and Public Health England as well, who've worked with in the past on blood spot testing. So please feel free to email me any questions. Thank you very much for your attention today and for attending this webinar. And please note that we do have other webinars as well. We have a series of webinars through the year. So please feel free to have a look at our webinar schedule and join us if there's any of these that are of interest. I'll be presenting more webinars on the MVX 7100 later on in the year, and there's particularly going to be one on geochemical testing, probably around about September time. So thank you very much for your time and your interest, and I look forward to hearing from you. Thank you very much.